We're going to spend a little time talking about charging methods. You spent some time on the Will That Be Cash or Charge lab, charging different types of materials that you had around the house. We're going to describe each of those. So on page 4 in your yellow packet, there's a table that looks like mine that's on the screen. You can use that to record a few notes just to kind of collect your thoughts. I'm going to be bopping back and forth between that and this app that you looked at. And so the first thing that you did when you got onto this app, or maybe at home, like the picture that I had up on the Google Classroom, is so I take this balloon and I rub it on my sweater. It now becomes positively charged and my balloon becomes negatively charged. And no surprise, if I let that balloon go, it attracts to that positively charged sweater. I want you to notice a couple of things. First is, what moved? Did the protons move? Absolutely not. They did not move. Well, why not? The protons are deep within the nucleus of an atom. They are stable and stationary for most atoms. And so if you think back to your chemistry, we know that that nucleus is really what tells us what the atom is, right? The number of protons dictates the element on the periodic table that that object is. And therefore, those protons are so buried deep within there, a simple like pulling a tape up off of a desk or rubbing a balloon on a sweater or onto your hair isn't going to move them. We have to have big things like accelerators, like particle accelerators, to get into the nucleus of an atom. And then if we look at the electrons, some of those electrons are way out there. Think about those electrons in those outer shells. They're quite a bit ways from that center of the atom, and so they're a lot easier to move around, which is exactly what's happening when we rub our balloon onto our sweater, or we take our tape and pull it up off the table, or we rub some wool onto a comb or a plastic ruler or something like that. And as I took that and rubbed that, we noticed that the sweater became positively charged because it has a deficit or a deficiency in the number of electrons. So it's a deficit, it's missing electrons. Where the balloon here, it has a negative charge because it's acquired electrons. If we go back to this table, we're going to start looking at this row called friction. So this is what happened when you rubbed two objects together or you pulled the tape up off the table. So let's write a description down. This is going to be two uncharged objects that are rubbed together. And if you want to make a couple of notes here, that would be excellent. Maybe you could write in that this was the balloon rubbed on the wool or the tape pulled up from the table. So we have two uncharged objects that are rubbed together. And then, and to be clear, an uncharged object is these two objects that have both a balance of negative charges and positive charges in them. Right? Both the balloon and the wall have a balance of those negative and positive charges within them. We call those objects uncharged. Sometimes we call them neutral, but I find that confuses students in that sometimes they think it's a type of charge, and it is definitely not. So it is an uncharged object or a net neutral charged object. So we rub those two together, and there's definitely a transfer of charge. So that middle column asks, is there a transfer of charge, yes or no? Well, definitely. Those negative charges were transferred from the sweater onto the balloon. So what's the resulting charge there? If I can find my mouse here. The resulting charge were the balloon has same size of charge as the sweater, but they are opposite. So one would be positive and one would be negative. But they have to be the same size, and they have to be the same size because charge is conserved. That's another property that we learned in chemistry, right? We can't make charge, we can't destroy it, we can move it around, which is essentially what's happening when we rub the balloon onto the sweater, right? Every electron that is coming off of the sweater is going onto the balloon. The next type of interaction that we're going to talk about is what makes the balloon stick to the wall. So if I take this balloon and I stick it over onto the wall and I let it go, or I get it close to the wall and I let it go, notice it sticks to the wall, but I have to get it pretty close. What's important here is what happens to the charges within the wall when the balloon comes near it. So take a look. Now, as this balloon comes closer and closer, what happens to those negative charges within the wall? Right? There's no transfer of charge, but they're pushed away. And that's what an induction is. So if we go and look at this very last row, an induction is when you have a charged object brought close to an uncharged object. So if we want to put like parentheses in here so we know that this is the balloon, brought close to the uncharged object, like the wall, the charges, and I'll say the negative charges within the wall, rearrange themselves. And we saw that. We saw those negative charges being pushed away, right? We see those negative charges being pushed away from the place where the balloon is. We can even move that balloon up and down. We see those charges respond. Now notice those positive charges stay put, right? We noticed that before, that those positive charges stay put. And since these positive charges are much closer than these negative charges, that balloon sticks to the wall. So that rearrangement of the charges within the wall is called induction. So is there a transfer of charge? Definitely not. No. So we have no transfer of charge. And so if we look at that very last column is the resulting charges on the objects. The resulting charges on the objects would essentially be the same as before. There is no change in the net charge on those two objects. If we think a little bit more about charge, I'm going to come back to contact. We will talk about contact a little bit later. But if we come back here and we look at those charges on a single electron. So we were talking about the electrons coming off the sweater and moving onto the balloon. The charge on a single electron or a proton is this fundamental charge value. Again, you probably saw this number in chemistry. It's 1.602 times 10 to the negative 19th coulomb. So that capital C is a unit of a coulomb. Now, the coulomb is an extraordinarily large amount of charge. So the unit that we use to measure it, it's named after a guy, as always, a physicist. That capital C stands for coulomb. So if you had a dump truck and you fill that dump truck with sand. So if that every grain of sand represents an electron, a coulomb of charge would fill an entire dump truck. So it is a really, really, really big unit of charge. So when a single electron has a little teeny, right? This number right here, this negative 19th, tells us that we have a little bitty teeny amount of charge that is stored or is on an electron. The charge on an electron we know is to be negative. And the charge on a proton is again going to be positive. The charge on both an electron and a proton are the same size. They're just different. One is called positive and one is called negative. If we think about rubbing a balloon onto our hair or onto our sweater, we certainly are not moving a dump truck's worth of electrons in that, right? We're actually moving very small quantities. So we're going to have to use some pretty small prefixes. So it's been a while since we've looked at these, and remember our very first unit, you can go back, it's pink in that packet. It has all of those prefixes on the very front of that packet. So everyday charges that we see when you walk across the carpet and you touch a doorknob and it gives you a little shock, or you see the little sparks in the blankets as you pull them apart in the wintertime. They're really, really small, so they're much smaller than that dump truck filled with sand. So we'll use the metric prefixes of nano, micro, and pico. And you see those, what those represent there. And you should notice this guy right here, right? He looks familiar. We've seen that Greek letter. It's a mu, that U with a fun little N extra tail. We use it, I believe, for our coefficient of friction. So let's do just a very quick example. And that very quick example that we're going to do is this one here. So when you rub the balloon under your hair, it acquired a charge of negative, because it acquired electrons, negative 9.65 nanocoulombs of charge. How many extra electrons were on that balloon? All right, so let's go back and let's look at this idea. This charge on a single electron is 1.602 times 10 to the negative 19th coulombs. Okay, we're going to need that number. And then we're going to bring that forward. So what I'm going to ask you to do right now is take a moment, and I want you to give this guy a shot. Just try it, fool around with a little bit. Notice that this is in nanocoulombs, so we'll have to use this metric prefix. We'll also have to use that definition of what is a charge on an electron. So take a moment and give that a shot. All right, so to finish this up, notice that I've changed my charge of the 9.65 nanocoulombs. I went ahead and I put that into my I went ahead and put that into my scientific notation. Remember, our nano is times 10 to the negative 9th. Also, you'll notice that I dropped my negative sign off. We just want to know how many extra electrons. We already know that that charge is negative, so I just dropped that. I'm going to use that stoichiometry language like times in a line, and the easiest way that I can tell you to do this is to set it up like a stoichiometry problem. So I need my coulomb to cancel out. I'm going to put that down on the bottom. I want the number of electrons, so I put that on the top, right? And I know that one electron has a charge of 1.602 times 10 to the negative 19th coulombs. And I kind of went over that, but I think you can read that okay. So then we just do our math. So essentially what we're doing is we're just taking our 9.65 times 10 to the negative 9th coulombs and then dividing that by our fundamental charge. So take a moment, calculate that out, and come right back in just a moment. All right, what did you get for your answer when you divided those two out? Any surprises? 9.08, or yep, 9.08. And I'll round it up to 9.09 times 10 to the 10th electrons. That's a whole heap of electrons, but that's still a whole lot less than that dump truck full. Awesome, awesome, awesome. Okay, so I'm going to have you try a couple of things for me. So I'm going to have you try page 7, which is a section review, numbers 1, 3, and 4. So with what we did today and the work that you did before, you should be able to finish that. And then I'm also going to give you another assignment. So I'll post all of that on Google Classroom, and I will be back in a couple of days to bring together a few conclusions from the next assignment. Have a great day, and I hope this video finds you all doing well. Miss you all. Bye.